Now, the question that comes up for me, given that I know perfectly well, I just kind of guessed at what a good line, a good fitting line would be for that data. The question arises how good a job I did coming up with that line, and is that line that we came up with the best one? Does it best fit the data? Now, if we compare the predictions of our linear equation with some observed values of the variable y, remember y stands for the distance traveled by the golf ball, we find that there are errors. These errors are called residuals. So, for example, let's consider golf swing speed 103. Now, our linear equation predicts that the y value will be, let's see, we had 2.83333 times x, and we're using 103 for x, and then we had minus 22.4967. 4967. Okay, so we get, in this case, 269.3 yards. But if you go back to the scatter plot, or maybe even better would be to go back to the data, for 103, for swing speed 103, the actual observed value was, what was it? It was 274. Okay, so the actual observed value when x is 103, the actual observed y value is 274. The number we're getting is the y value on that line, which we're using as sort of an approximation of the actual, or a prediction of what you would observe for a y value there. So on the line, the y value that goes along with 103 is 269.3. So that's off from the actual observed value. The amount of error, let's compute that. Okay, so the observed value is 274. Now, the error or residual will always compute by taking the observed y and subtracting the predicted y. So the observed value is 274, subtracting the predicted value, predicted by our linear equation or linear model. Let's see, that works out to be 4.7 yards. Okay, so the difference in the y values, so in other words, the length of that line segment is 4.7 yards. Again, that's known as a residual. That's the error between our, or difference between our model, this line, and the observed value. Okay, so the point I'm making here is that there are errors. Okay, there's going to be differences between the model, the linear equation, and the observed value. So what we would like to do is, first of all, what's this best line that I'm looking for? Well, it kind of makes sense to have that be the one that makes the total of the residuals, errors, differences between the prediction and the observations, as small as possible. Okay, so I want a line where if you looked at all of the residuals, so all of these errors, that one, plus that one, plus that one, plus that one, I want the totality of the residuals or differences to be as small as possible. That's what I'm going to think of as the line that best fits this data. Now, the issue with just adding up the residuals, we have this issue again that the ones that are when the observed data value is above our line, you get positive residuals. If the data value that's observed is below the line, you get negative residuals. So they're going to offset each other some. And so what we need is a way of making all the residuals positive so that they don't that they're not balancing each other out. We had that same issue when we calculated standard deviation. So we're going to basically do the same thing we did with standard deviation. We're going to, so that we have positive numbers, we're going to look at the squares of all the residuals.